Atoms and elements are the things that we find in the periodic table. Probably the most important thing is that atoms form compounds in whole number ratios. And that will lead us to a couple different things. So the law of definite proportions. And let's say we're looking at H2O. If we've got an H2O, first of all, we know that there's two H's. And we know that there's one O. From here, maybe we know that there's 2 grams of H. If that's the case, then we know that there's going to be 16 grams of O. This also means that we would have 2 moles of H and 1 mole of O. We'll get into what those moles are. From here, we might be able to calculate something called the mass percent, because we can see how 18 is the total grams of this mole of H2O. If we have 1 mole of H2O, 1 mole of H2O, then we'll be able to say 18 grams. So this 18 grams is 1 mole of H2O. So we can calculate the mass of the element divided by the mass of the molecule. And so in this case, you could do 2 divided by 18 or 16 divided by 18, and you'd figure out the mass percent that that particular element would have in the molecule. Here, let's also move on to the law of multiple proportions, because let's say we have carbon monoxide or carbon dioxide. We can compare these 2 molecules. The law of multiple proportion is for comparing multiple molecules. So we can compare these 2 to each other and say, okay, if we have 12 grams of C, we'll have 16 grams of O. But in this one, notice we would have 12 grams of C and we would get 32 grams of O, because we have twice as much O. So the law of multiple proportions for comparing multiple molecules to each other, whereas a definite proportion is for just comparing within that one molecule what's going on within that. We should be able to read a periodic table. We have the element here, C, which is carbon. At the top, we have this number 6. This is the atomic number, Z. And then at the bottom, we have 12.011. This is the atomic mass. This is going to be an AMU. And this is the mass of one atom. Mass of one atom. The atomic number, Z, is going to be the number of protons in the element. And we also have the mass number, which you might see, this is the letter A, which is the protons plus the neutrons. And then we might even know ion charge. If an element gets charged, then this is the protons plus the electrons. Essentially, the difference between that is going to give you the charge. Now we have these things called isotopes. Isotopes are going to be the same element, and they even have the same number of protons, but they have a different number of neutrons. So they're going to kind of have different weights. Well, we can write out these isotopes in 2 ways. We can write it in hyphen form, which would be something like carbon 12. Or we can use nuclear form, which is going to be like, say, 12, 6, and this would be A, and then Z, and then here's your element. It's just how to write the isotopes. But the number of the isotope here is going to be the weight in AMUs. So isotope weighted average. If you take the isotope weighted average, you'll get the atomic mass of the actual element. So we'll take carbon 12 and then carbon 13, and then we're going to take the weighted average of these 2 This one's going to have 98.9% components, or it's going to be found prevalency in nature. Like this is how often it's found. And over here we would find this about 1% of the time. And so therefore, if we take the 12 AMU and the 13 AMU from these two isotopes, we'll take the weighted average of that and we'll find that it's usually that you'll find carbon being about 12.011 AMUs in nature. Now ions are going to be the same element. They have the same number of protons and neutrons, but they have a different charge. And so let's say we'd have a plus charge, that would be a cation. That means that they lose electrons. Since the electrons are negatively charged, if you lose electrons, you're going to get plus charge. For the negative, that's an anion, and that's when you gain electrons. We can use a mass spectrometer to determine the mass of these ions, because the deflection depends on the mass over charge ratio. And a mass spectrometer works by shooting ions through a magnetic field. Shoot it through some magnets, then it'll deflect depending on the mass over charge ratio. A molar mass is a key to being able to do a lot of these conversions. Well, we're going to take the sum of atomic masses, and then we're going to just convert it straight to grams, and then we're going to put that over 1 mole of the element. So for C, you take the sum of the atomic masses, which is 12, and then you just put 12 grams per mole, and that's going to be the conversion factor for C. For carbon monoxide, you take 12 grams and 16 grams, and that would be 28 grams per mole of carbon monoxide. So that's molar mass. Now the mole is 6.022 e to the 23rd. This is Avogadro's number. It's just a number, but essentially what that represents is the number of atoms in 12 grams of carbon 12. So let's take 12 grams of carbon, and then we'll have to convert that to 1 mole of carbon, because 12 grams per mole, right? And then we can use Avogadro's number to tell us the number of atoms. So in order to follow this process, we use the molar mass here as a conversion, and then we use Avogadro's number here in that conversion. Now let's take a look at the properties of protons, neutrons, and electrons. This is one of my favorite charts. We have 1.67 e to the negative 27 kilograms for the protons, that's the mass. 1.67 e to the negative 27 kilograms for neutrons. 9.11 e to the negative 31 kilograms for the electrons. Protons are 1 AMU, so are neutrons, but electrons are basically 0 AMU. Very, very, very small. The charge on the proton is positive 1.6 e to the negative 19 coulombs. Neutron has 0 charge, and the electrons have a negative charge of 1.6 e to the negative 19. Now let's look at the structure of solid matter. Say we have our positive nucleus right here, and we have a whole bunch of negative electrons kind of floating around. And then we'll take maybe another one of these elements, these atoms, and we'll bring it closer. But it's going to want to chill around those negatives over there. And then it will throw up its negatives around that positive. And then we'll have another one kind of come by here as another positive, wants to hang out by those negatives, and it'll throw its negatives around there. And you might notice that this is going to be a little bit difficult to break apart. And so that's how we get solid matter. Also, another cool diagram to look at is if we notice the periodic table has a little staircase like this is where we're going to find the metalloids, and that kind of is in between the metals and the non-metals, which we'll take a look at in just a second. Now, metals like to be positive, and that's because metals like to lose electrons. They're good conductors, they're malleable, and what that means is it's easy to work with them, move them around, and they're also ductile, which means that they're easy to string into a very straight, thin wire. And then we also have nonmetals, which like to be negative, because these things tend to gain electrons, so they're not conductors. But they could be solid, liquid, gas. And then we also have this third category, which is the metalloids. And these are basically, they could do either one of those things. They've got properties of both. And they're semiconductors. Now, the periodic table is arranged based off of periodic law, which states that the elements are in order of the number of protons. And we've also noticed that there is a periodic repetition of various properties, and so that will form columns and rows. So for example, we have the alkali metals. Those are going to be in column number 1. They're very reactive, especially in water. Column number 2 is going to be the alkaline earth metals. This has some reactivity. Then we can go to the halogens, which are column 17. They are just barely close to being a full outer shell. So these are also very reactive. And they might even be lethal. You'll notice that the ones that only require shifting one electron, either losing one or gaining one, will be very, very reactive. And we also have the noble gases. And since these have a full shell already, these things, they're not even going to really react with anything. So they're basically colorless, tasteless, odorless, and they are least reactive because they already have a full shell. And we also have things like transition metals. That's basically everything else in the periodic table. These are going to be stable compounds. Like, these form stable compounds, and they also have various ions. This is going to be most of the stuff that we have in the periodic table. But then there's also lanthanides and actinides, and these are radioactive. That would be the last couple rows in the periodic table. Let's remember that in column 1, these elements lose one electron, and so they'll become positive. In the second column, these will lose 2 electrons, and so they'll become 2+. In row 16, that's when you start to gain 2 electrons, so you get 2-, and in 17, one before the last row, that's when you're going to be gaining 1 electron, so you get -. And again, these ones were going to be the most reactive, the ones that only gain or lose 1 electron. Now, if you enjoyed chemistry, there's a lot of famous experiments that we could research, such as Brownian motion, how they discovered atoms, right? And then there was the cathode ray experiment. This is how they discovered the electron. There was the Millikan oil drop. This is where they discovered the charge of the electron. Then we had the argument about the structure of the atom. So there was the plum pudding theory that got proven wrong by Rutherford's gold foil experiment. And that's when they kind of shot particles, alpha particles, at this gold thing, and they discovered that by the deflection of the alpha particles, we noticed that there was mass in the very center of the atom of gold, but there was nothing on the edges, and that's how we discovered the structure of the atom.